Everyone, I'm going to pin my video so that I can see the big picture here. This particular workshop is going to be one that is participation oriented. So if you didn't download my handout, you will need a blank piece of paper and preferably some colored pencils, but you can do it with just a pencil for what we're doing. But you will be participating because I want you to experience the efficacy of some of the strategies I'm going to be giving you. So this will be more participation oriented, I think, than many workshops that you've been attending. If you downloaded the handout, on the back of the handout, there are squares for drawing as a drawing canvas, and I'll be addressing that throughout. So I hope that you'll really enjoy this. This is the perfect storm when reading and math meet. And I will tell you that one of the reasons I'm addressing this is that I'm not only a math consultant working in the field of math for the last 30 years, but I am also a certified academic language therapist. So this is going to be a little different than you've seen elsewhere. If you hear rumbling, it's because where I am, there's a thunderstorm going on. So if there's a blip in the electronics or something, be patient. I will be right back. So the perfect storm when reading and math meet. In this multisensory approach, I want to tell you I've based this presentation on the intersection of math and traditional multisensory instruction, both literacy and math. The evidence from the Institute for Educational Science, the What Works Clearinghouse Practice Guide, particularly the one that was updated in 2018 on problem solving, best practices in math from the NCTM, and evidence from neuroscience, not only the imaging studies, but the cognitive science. First of all, let's talk about the obvious. I deal a lot with students who have learning challenges. Many have language-based learning deficits and have trouble with, wait for it, language. Receptive, internal and external, expressive, internal and external. And when I say expressive language internal, what does that mean? That means the do you talk to yourself? That internal monologue that a student uses to monitor their processing of information. They are talking to themselves, often internally and silently. You can't hear it, but they're talking to themselves to monitor themselves. And the issue is if you have a student who has word retrieval or word finding difficulties, halting oral language skills, they're going to be talking to themselves with the same language they would use orally. And we can't dismiss that. So that word finding or processing deficits in language will actually impact them with the internal monologue. We also have students who are second language learners. I had this verified just this year by one of my doctors, my neurologist. And we were talking about my work, and I said, let me ask you, when you are thinking about math, do you calculate in English? And she said, well, yes, I think I'm totally, fluent in English now, and I do everything in English, except when I multiply, I switch back to Chinese. Now think about that. We know from the neuroscience that when we move from numeracy-based calculations to multiplication and division, that we begin to use more of the language hemisphere of the brain. And Dr. Shaywitz, in her work on dyslexia, says that students who have language-based processing deficits may struggle more with retrieval, organization, and expression of language. And we know that from, there we go, multiplication is a language-based and a language retrieval activity. That speaks to developing fluency, but also to monitoring our calculations as we're working through things. Decoding can be an issue, and many math teachers think that a problem with word problems is because children can't read the words, and that's sometimes the issue, not always. Prosody, for if you're a math teacher and you don't know what prosody means, it's the inflection with which we speak. It's how we group words together for units of meaning and clauses and phrases. And when we are speaking, the slight processing pauses that we would write as punctuation, we do naturally because that's the cadence with which we speak. Students do not always read that way, and they need explicit instruction in doing that. Another issue is working memory. We know that many of our students with learning challenges struggle with working memory. Story problems, problem solving, places additional stress due to the demands of not only decoding, but deficits in working memory, reading fluency and prosody, reading comprehension, math fact fluency, sequencing for Pete's sake, coding, writing things down, and executive functions. And it's amazing that we can even do this. Dr. Cheryl Chase says, in the mind of a student with learning differences, it's like trying to cook Thanksgiving dinner in a camper. There's only so much room and too much going on. And so sorting all that out for our students with disabilities in particular can be a real challenge. Recent evidence suggests that weak working memory is a contributor to difficulties in problem solving. Go figure. And students access the visual hemisphere of the brain when calculating and solving word problems. And so that visual access can be a possible strength. And yet, too many times when we're doing, if this word says this, you do that. We heard this morning, Dr. Hughes told us, don't do the keyword strategy as if you see this word, do that. It simply doesn't work sufficiently. And we don't want to have that rule that expires. So in the Institute for Educational Science Practice Guide, Improving Mathematical Problem Solving, grades 4 through 8, the two recommendations that received strong evidence for their support are the two that are not often addressed when we talk about word problems. And yet we should look for that strong evidence basis. Assist students in monitoring and reflecting on the problem-solving process. I'd like each of you to think for a moment about that sentence. What does monitoring mean? And what does reflecting on the problem-solving process mean? And as we were just saying prior to starting this session, when teachers and administrators and coaches interpret the evidence and how they implement it can vary widely. So we can all talk about evidence-based strategies, but do we all see them as the same thing in the classroom? And do we implement them in the classroom in similar ways? So monitoring, that's as the problem-solving process is going on. That self-monitoring is a very important feature. And what does reflect mean? It means think about it. And when we think about it, we often visualize it. And the second recommendation is teach students how to use visual representations, not just give it to them, but ultimately in math, we want our students generating the math. We want them to come up with the representations. We want them not to just use a canned model that we've given them, but when they create their own visualization, they are showing that they comprehend. And that's a formative assessment. If the model the student creates isn't accurate to the problem, doesn't accurately represent it, then there's a comprehension issue, and we need to deal with that. So the supports for students with disabilities in problem solving include, we can change names. We don't have to use names that are not decodable. We can choose problems that are relevant to the students and their environment, their experience. We can use friendly numbers. We can practice sub-skills like operations. We can use a larger font and fewer problems on a page so that the student who has dysgraphia, who has figure ground difficulties, has workspace and white space. I've seen 4th and 5th and 6th graders who write such large font in such a large font that tests and paperwork and worksheets are not formatted for them. So we can use a larger font, 28 font or more. We can use fewer problems on a page so that they have that clear space to focus and do their work. And some students get a reader as an accommodation. And I want to speak about that for a moment, for both reading comprehension and especially for math. For a student with processing deficits, we offer as teachers in our instructional speak speech, what I call processing pauses. After a unit of meaning, we stop and just give the student a moment to hear what we've said. For the student with working memory issues, if we talk too fast, the language just goes right over them. So we need to moderate our rate of speech, offer processing pauses. And if a student has a reader, that student has the right to speak to an adult reader and say, could you pause and give me a chance to understand that? That's self-advocacy. So we don't want an adult reading to a child or an older student who reads straight through and says, okay, do you remember it all? It doesn't make sense. So we're teaching that metacognitive piece for our students to be able to advocate for themselves and say, could you just stop right there and let me do some calculations, or let me draw, or let me reread it? Could you reread that sentence? So unlike a reader who might read a literacy text where they would read right through and phrase appropriately for the student to get the picture of the action of a story or a paragraph, in math, think about it, we often have to act on every sentence. We do not do that in prose. And math word problems are not written out like recipes with step 1, step 2, step 3, step 4. We have to generate that. And the student must be able to see that, especially as they get older and the problems become more complex. So the supports we give them are pretty obvious. We can prepare younger students in grades kindergarten through 2 by simply putting numbers and a word or numbers and a picture. 2 apples plus 3 apples. We're preparing them for that linguistic aspect of word problems. Practice the oral language skills associated with problem solving. Have them speak in complete sentences. Use pictures or prompts before decoding skills can be used. And so my mentor, Dr. Joyce Steeves, used to say, just give them pictures and or words. I can show 2 apples plus 3 apples, and the apples can be either pictures or words. And apply your evidence-based strategies even before text is included. Have students self-monitor. We always want high-level thinking and reasoning. Have them draw, have them plan, have them evaluate the schema so that they get an idea. And as Dr. Hughes said this morning, there is evidence that gestures are good. So as I said yesterday, the addition is putting together and subtraction is taking from. That's our first iteration before compare. And multiplication making many and division separating apart. Those gestures can help anchor meaning and also help them identify the schema. I'm going to go through this quickly because we've had lots of this at the conference, but we know that the science of learning wants to identify the effective strategies based on the underlying cognitive processes involved in learning. We're working on memory formation, attention to details in what we're learning, retrieval of that information through interleaving and spaced practice over time, and problem solving. We want to translate all that into actionable teaching practices. We want to optimize those learning outcomes for our students. Now, I'm going to give you these quickly, and they're in the handout. Spaced practice over time, revisit information to supply that repetitive practice students need to develop mastery. Interleaving, bring things back from ages ago, weave it into your current instruction to maintain it and to give a deeper understanding of how connections apply. So if I've taught addition thoroughly and now I'm going to subtraction, I want to go back and revisit a concept. Review fractions before you're teaching decimals or while you're teaching decimals. Look for those linkages through the vertical hierarchy of math. Metacognition, we're teaching our students to see what they need to do. Retrieval practice, actively recalling that information. I want to talk just a moment about dual coding, the dual coding hypothesis, where we wed language to images. That image can trigger retrieval for words, as rhythm can. Linking from known to new with elaboration, and using our concrete examples within the student's experience. So in the What Works Clearinghouse Practice Guide, students with disabilities, the one for helping students with disabilities, that they need practice with typical word problems for what you're teaching at that moment. That's your blocked practice for interleaving. Lots of practice with typical word problems and the language associated with them. Students with disabilities need multiple representations that we've seen many of our speakers talking about CRA or CPA instructional sequence. Proved by construction. Remember, manipulatives are not inefficient calculators, and the goal of using manipulatives is to get rid of them. But prove by construction, solve the algorithm, and then prove your answer with manipulatives. Or prove something with concrete and then write the algorithm and it steps out. That's that worked model, but in a different representation. So the What Works Clearinghouse Practice Guide on Problem Solving was updated in 2018. There were 5 recommendations. They varied from strong to moderate to weak evidence to support their use. The link for that practice guide is here. But I want to look at the 2 only, especially the 2 that receive strong evidence. And that's why I want you to look at those words. What does it mean to monitor? What does it mean to reflect on the problem-solving process? And how can we use visual representations? Think of your students who have limited English proficiency, and yet they can see the math. They know how to do the math, but the English words are getting in the way. Think of your students with limited oral language capacity. They may not have the vocabulary to express what they need to express, but they can see the math. So now we have audience participation time, and we're going to unlock the power of the pencil. So get your drawing canvas, get your colored pencils, and/or your pencil or pen. Are you ready? We have comprehension problem number 1. This is a grade 5 word problem. A pan of brownies was left out on the counter. Please draw something. Have you ever seen a pan of brownies? I've been baking since I was 4 or 5 years old, and I can tell you what kind of pan we use to bake brownies. Draw that visual representation, because the first sentence of a word problem is often setting the context for the problem. There may be no numbers involved. We're not talking about, is this relevant information, not relevant information? We're talking about brownies here. 1/4 of the pan had already been eaten. How does that change your drawing? And I will be switching to my document camera on this presentation as well. So I'm going to be drawing along with you, and I'm going to show 3 different representations of this problem that a student might draw. And depending upon what you draw, I may be able to tell the type of curriculum that you are teaching from. Okay. Alex came along and ate 2/3 of the brownies that were left. How does that change your drawing? Now, some of the language of our fraction instruction can help support that. What does 2/3 mean? It means 2 of 3 equal parts. I'd like you right now in the chat. I'm going to stop sharing a moment, turn on my chat so I can see it. I would like you to turn on the chat. I'll go back to that right now. And if you think you could generate a question that could be the question for this problem, reasoning what you already have there, what kinds of questions could we ask? What might we like to know? Type it into the chat for me, would you? And for some reason, it's not showing up on here for me. Let's see. There we go. All right. So we have a good question here. How much of the brownie pan was left? What, Maggie? What a great question. We certainly could ask that one. How much of the brownie pan is still left to eat? Great. How much of the brownie pan is still left? How much of the brownie pan is still left? How much of the original brownies are left? What fraction of the brownies are left? Now, remember, this is fifth grade. What fraction of the brownies are left to eat, are left to eat? Wow. What fraction of the original pan did Alex eat? Could you answer any of those questions from your drawing? Okay, so we might want students to reflect upon the meaning of a problem and try to generate some of their questions. And indeed, the question is, how much of the whole pan of brownies did Alex eat? Could you type your answer in for me into the chat? How much of the whole pan did Alex eat? Very, very good. I have some genius in the room today. You guys are really on target. Now, I want to tell you that when I give this particular problem in workshops with elementary teachers, with parents, with the community, I frequently have people who get this answer correct. And I'm going to ask you now, do not type it into the chat. Would you write down the mathematical equation that this word problem is asking our students to generate? What is the algorithm? Because I have teachers who cannot tell me the algorithm, though they solved this problem with a picture. And the reason is that this is a two-part word problem. In order to solve this part of the problem, you have to identify what was left. And it doesn't explicitly give you that. You're absolutely right. What is 2/3 of 3/4? Now, many fifth graders will not be able to generate that equation, but they could solve this problem. And that's where we're starting today. So, teach your students to adapt visual representations. So the instructional sequence, concrete, representational, abstract, you've heard a lot about in many of our presentations, does support building visual accuracy and imagery for students. The old Rational Number Project from the University of Minnesota actually said that initially circular models for fractions were really good. And then we want to transition to get them out of those unit fractions of 1/4, 1/3, 1/2. We want to use things like hexagons and bar models and number lines, absolutely. But the initial instruction, and some of our students with a more primitive, immature sense of fractions may prefer circular models. Again, that's the formative piece you're looking for in your students. So if I were to ask my students to show me their representations, could we discuss them? Could we talk about what those representations are? Here is my 9-inch by 9-inch square brownie pan. Some students may prefer circles. Some may prefer a bar model. With younger students evaluating this, can you see how this one is a little more difficult to see that Alex ate 1/2 of the pan in that bar model? And also seeing it on a number line might be problematic for some students, but almost all the students can solve it with one of these models. So keep in mind that using visual representations can be a really promising model for many of our students, even in early grades. So I'm going to be applying some of this at lower grades, even though the problem-solving guide was for 4th grade and up. So explicit instruction and accurate drawing, as you go through perhaps that CRA model, we will cut things for fractions. Certainly, we're going to be using base 10 blocks, and in my case, craft sticks, but we're going to solve things with pictures and often simultaneously with a number line. So here's 5 groups of the quantity 3/4, and then I can see how it's simplified as 3 and 3/4. And this is actual student work, you can tell, because the student crossed a lot out as he was reasoning. So doing things with pictures can be very beneficial for students. Efficient representations is the other piece. We want to say to our students and give a model of this. You're not Michelangelo. This is not the Sistine Chapel. We're not putting fringe on the pencil bags. Your drawings need to be simple shapes, dots, circles, boxes, rows. This is what in literacy we would call coding. So rather than writing or spelling, we're drawing efficient visual representations that are not super artistic, but that help us to see the concepts, the quantities, and the magnitude that we're dealing with in these representations. So here's our second one. Are you ready to draw? Second drawing canvas. Audience participation time. Robert is buying Valentine's Day treats for his 2 dogs. From the information you're given there, what could we draw? Because we're not going to draw a dog. That's the Michelangelo version. Could we draw the dog bed? And how many do we draw? That's the information we're given, and we have the context of the problem. Now, one gentleman in one workshop read that first sentence and he said, well, I can tell you that's just sad. He wants to buy 3 dog. Well, gee, I don't know who writes these math word problems, but most second graders are not decoding French Latin digraphs. So biscuits would be a word many of our students might stumble over. And they might also stumble over sweater. So, gee, what could I do? Well, we know buy 3 dog somethings that starts with B. Could you put a B and that number of B's on each dog bed? We're teaching them actually to use variables at this point because I couldn't read that word, but I knew he bought 3 somethings. And he bought an S. He brought something that starts with an S for each dog. So now you've got that picture of the dog beds with 3 B's and an S on it. What could the question be? Could you type that into the chat? What kind of question could my students think we could ask for this? Even at the second grade level. How many items did he buy in all? Amy, you're right on target. How many did he buy altogether? Total items. Is there another question other than the total items that could be asked there of a second grader? How many bees did he buy? Right. How about how many gifts for each dog? There's a lot of ways this question could go. You're right. How many gifts in all? How many more B's than S's? We could ask all kinds of questions, but you're right. On this one, it was pretty simple. It was how many items did he need to buy? But you see the variability of reasoning that from the images that the child creates with simple images and efficient images, that child can solve that problem. So if the problem is decoding, you can use decodable texts as a modification. You can also teach them, that structure of the language, the grammar and syntax, that when I say he bought 3 of something, that thing is a noun. Dysgraphia and fluency, we can use simple drawings, ample white space, combinations of coding and shapes. We don't always have to draw an object. We can use a letter, a number in a circle or a box, anything that helps us code or organize our thinking. Not always just a graphic organizer, but a visualization that makes sense to the child. And then the piece I really want you to notice is that comprehension or prosody element, knowing when to pause to let the unit of meaning jump up and stick out. And for children with working memory issues, stopping periodically, not reading the whole problem. Because reading the whole problem first to understand it means you're employing working memory and too many words for many of our children. So when you are lumping so many words together for meaning and pieces with different contexts, many of our students get lost. And I can tell you for many of my language-based learning disability students, when they look at that word problem, they say, mark C and move on. So we can use that incremental reasoning and drawing and calculations as we go along. Yes, the arithmetic and fluency, strategies for constructing facts or near point references, or generating facts based on others, those strategies can all help. I've seen fourth graders come in drawing lines and adding them, and then not drawing too many lines for multiplication, and they can't separate them out. So your drawings must be efficient for the concept you're doing. So what tools are going to aid students in accurately visualizing these quantities, and how are they manipulated? So as our stories become exclusively based only on words, or a combination of words and meaningful visualizations, they're based on accumulated experience. Now, our first superpower that takes us to middle school is that numeracy, subitizing, and pattern recognition, where I can create these visual patterns for doing my mental math. My second superpower is that place value in expanded form, knowing how to compose and decompose numbers to work with them flexibly. Flexible thinking with quantities is one of our cornerstones. And our third superpower, as you all may have heard, is that distributive property with multiplication and division. So I know you all know your 17 times table. So let's do a little mental math here together. If we know that 3 times 7 is 21, let's do 3 times 17. I want you to use your hands like this. This is a gesture. I want you to take 3 times the 10 is, and hold that number in working memory. We hold it in working memory by saying it 3 times. 3 times 10 is 30, 30, 30, 30. And 3 times 7 is 21. Put the two together, 30 and 21, and you have an answer. Let's do 5 times 17. 5 times the 10 is, 5 times 7 is, put them together, and now you've done 5 times 17. Now, 7 times 17 is a little more problematic. So I'm going to ask you to use your first superpower as well. We're going to do 7 times the 10. Hold that number in working memory. Say it 3 times. And then 7 times 7 is 49. And to put that together, we have to be flexible with numbers, because 70 plus 79 crosses the century. Can I break that 49 into friendlier, more flexible numbers that would help me get that answer? Why, I can break 49 into 30 plus 19. So 70 plus 30 is plus 19. And that is powerful for students. They don't always have to write the algorithm. They can think flexibly about numbers. As we move toward upper grades and middle school, we can now do 7 times 23. 7 times 20 will be very similar to 7 times 2. So 7 times 2 tens, or 7 times 20, is 140. 140. 7 times 3 is 21. We're holding that number in working memory. 140, 140, 140 plus 23. And now we have an answer. Let's take that a little higher. 1.5 times a number is all of the number and half again more. 1.5 times a number and half again more. 1.5 times 6 is all of 6 plus half of 6 more. 1.5 times 6 is 1.5 times 8 is all of 8 plus half of 8 more. Now, for some students, they're going to have to decompose to add. Keep that in mind. But 1.5 times 8 will be, and then we have to stretch them. Always stretch our students with a little bit of rigor. 1.5 times 800 is all of 800 and half of 800 more. 1.5 times 800 is, now if you said 1200, I want you to know that we are the only country on this earth that states the value in an improper form that needs to be simplified. It should be 1,200, not 1,200. But those gestures, as we practice and integrate with our students to get them to be more flexible with their numbers, it's going to help them do mental calculations. And it takes that load off that working memory as they are calculating. So those mental math strategies are very good. We calculate with minimal or no writing. And I love the way Dr. Myers in his last presentation was talking about that multiplicative inverse, the power of what one is, and the power of one to make our quantities reconfigured into different forms. So that's our fourth superpower that takes us to middle school math. Understanding the big ideas of math will benefit them, but they have to have a deep understanding of these. And as you bring those back through interleaved practice at the typical word problems for the concept you're teaching, but integrating these big ideas of math and flexibility, it reduces that load of working memory for the students who are moving on. So what gets moderate evidence is something that we all do. We expose our students to multiple problem-solving strategies. Why doesn't that get strong evidence? Well, we're hearing a lot of chatter that we don't want to teach our students 15 ways to solve the same problem. Again, it's too much clutter. It's trying to make Thanksgiving dinner in the camper. Having them reason and work collaboratively, task analysis, all of those things can help. But we want to make sure that our students get metacognitive awareness of what works for them. So problem-solving strategies can include the schema-based models. What I have found, though, is that for students with disabilities, when you add too many new words, you are losing some of your students. So, for example, total, difference, change, equal groups, comparisons, ratios, proportions, those obviously are taught incrementally through the grades. But for some students with language-based problems, matching the word problem to the schema is also an overload of working memory unless you scaffold it very carefully. And so I looked at a recent presentation of schema-based in preparation for today, and I have a full page of words. And for some of my students, the words are the problem. So we need to find other ways to either integrate all of the information or really be careful as we're teaching these new words and new strategies that our students really comprehend them. But no matter what strategy you approach, you have to plan. And so I looked at some of the schema-based approaches, which are great, by the way. It's helping students to really understand the math. But the first part is to read and understand the problem. This is where students with disabilities may struggle, not because of decoding, but because of working memory. They can't hold all that language in long enough to plan and organize. And you can give them all the graphic organizers you want and all the pre-made images you've got. But if they don't generate the image of the context of the problem from their own experience, it may not be as meaningful. So our culprits are working memory and processing speed and retrieval. So this is going to inhibit some of our students working efficiently through problem solving. So one common accommodation we use generally in special education is break large assignments into smaller, manageable units. We've all heard that. It's just like all students can't have preferential seating. But if the student reasons, plans, draws, and solves incrementally through word problems, they may be more successful. They may adapt and modify because they may reflect on that part of the problem and say, oh, I recognize the schema for that part of the problem. So we can use multiple strategies even within schema-based instruction. So here's another word problem you're going to draw. A third grade class decided to sell boxes of cookies to help raise money for a school trip. I can imagine right now some teachers saying, what's relevant mathematically? And they're going to cross out a bunch of words, and that's added words, added things. What word jumps out at you to draw? Can you draw a box? Simple, stupid, draw a box. Now let's modify that as we go to the next unit of meaning, as we break the word problem down into intimate little parts. Each box has 2 bags of cookies inside. How does that change your drawing? And our representations can be a mix of symbols, drawings, and also operations and calculations. We're just organizing. Each bag holds 14 cookies. Stop right there. No one of you is going to draw 14 cookies because we're working on efficiency here. How could you indicate that each bag that you've drawn has 14 cookies? What do you think, class? Write the number 14 in each bag. Now that is a simple drawing from which the student can reason. All right, let's see. Now we got a bunch more words. We're not even through reading the problem yet, but we have a representation that holds the information in mind so we can reflect on it. If each student needed to sell 4 boxes of cookies, now here's the English teacher coming out in me. Do you see that punctuation mark, that comma? It's an if clause called a dependent clause. They don't need to know that, but you do. It marks off a place where there is a subject and a verb, and each subject and verb is a complete thought, even though this is not a complete sentence. How does that, I'm going to pause there instead of reading to the next period, because that's like a stop, not a stop sign, but it's a yield sign. So each student needed to sell 4 boxes. What would you do? Here we have a lot of variability. A student may decide at this point to say, what I really think I want to do is I want to draw that box 4 times. So I could do that. What else could I do that would be efficient? I could say 4 boxes, or I could do some calculations before going there. What is 2 groups of 14? Well, I know that 14 is made of a 10 and a 4, and so I'm going to have 2 of those. So maybe before I even go any further, I want to calculate how many cookies are in each box. I have 2 10s and 8 1s. So that means I have 28. I can add it that way. Could I do the traditional algorithm? Sorry. I could. This is where the student makes a judgment call. But after performing calculations on the side, around it, they might say 28 cookies. They don't have to write the word. They can just put C. They don't even have to write the C. They just have to understand the meaning that that's a total of 28. Now we know that the student has to sell 4 of those boxes. How can I do that? Well, I've got 4 boxes, so I can do 4 boxes of 28. Many perceptive students at that point will say, I can identify this schema. This is going to ask me to do multiplication. So could I do 4 times 28? Yes. Could I do 4 groups of 28 by repeated addition? I could. Each student will choose what they want to do. Could I use a distributive property? Could I use an area model to do 4 times 20 plus 8 with my mental math? All of those are acceptable, but as the student reflects on the problem-solving process, that student can actually say, how would I solve the next step in that problem? And they will choose what they want to do to solve it. You have to give them the freedom to reason. And this is the point where students can say, let's talk about this. How did you solve that problem? And we validate their thinking. we validate what they're doing and they're solving, and we see that we all get the same answer. And if we don't, that's okay. Errors are our way to find out if our thinking is accurate in math. But these are really simple, they're not hard to teach, but just getting your students to solve the problems. So if each student needed to sell 4 boxes of cookies, how many cookies did each student need to sell? Now, think of your 3rd grade student who's reading that entire paragraph word problem and can't hold all that information in mind to solve it. So this is where read the problem, understand the problem, make a plan to solve the problem. Got students who cannot hold that in their minds long enough to do it, but they generate the plan, they generate the graphic organizer, they identify the schema, whatever method you're helping them to do, whether it's a schema based, a drawing based, they're organizing their thinking incrementally. You're scaffolding the ability. For your students who have attention deficits, this is really powerful. One of my practicum people likes to have them draw the circle around the period as a stop sign. And she has them use that acronym of, read, pause, or stop, and draw or calculate. I'm going to go through a sequence for that to sell this to the students. And it's based on a reading comprehension strategy. But because we have to act on every sentence, the student with working memory problems is at a distinct disadvantage. So prosody and signal words are if, when, before, after. All of those red light, green light signal words tell us where to pause to understand or comprehend the reading. This is even at the college level. It helps students to read with appropriate prosody. Clauses constitute that unit of meaning for information. So when we visualize, and here we go, you ready to visualize and draw again? Jamie has 5 meters. You can say yards if you are grounded in the standard system. 5 meters of fabric to make craft items for the fair. How would you draw that? Jamie has 5 meters. Could you use a number line? Absolutely. I like, for a primitive version, I like to have students draw shapes. And so I often will ask my students to draw a shape that they can reason from. And so my students might draw 5 circles, 5 boxes. And because when we buy fabric, in the context of buying fabric, you don't buy 5 individual meters. You buy one length of cloth that's 5 meters long. And that's a concept for comprehension. I can think about that. If each item requires 3/4 of a meter, and there's that comma, I don't want to read anymore until I think about that. What do you think that first part of this sentence is telling me to do? It means I have to create fractions the size of 3/4 as I cut them out of that long length of fabric. So you might have the student then draw, oh my God, a marker that's trying to die on me here. There we go. And so I might have the student might decide to cut each meter into fourths, but then I have that really important word each. How do I draw? How do I figure out to code or label or indicate that each group of 3/4 is distinct? This is where colored pencils and markers can be very helpful. So I might have the student or have them recommend, this is a great collaborative problem. And the student can color in 3 of the fourths on either the number line or the shape. And then color the next group of 3/4 a different color or shade it differently. Squiggles, circles, cloudy things, stripes, however you want to have that student color or indicate that each group of 3/4 is different. because we're trying to see how many pieces the size of 3/4 of a yard I can make from 5 meters of cloth. This is a difficult problem for comprehension for many students. And it's one of the reasons I like to use it, because when you draw it, it really isn't complicated at all. And your instructional language can help the student to really understand and reflect on the meaning of the answer. So I'm coloring my 3/4 groups in. I want you to do the same. And if you'd like to, try to put it on a number line and think of cutting cloth into 3/4 lengths of cloth. Just a second to let you color that in or draw it. And now we're going to reflect on not only how we did it, does it fit the context of the problem, but also what's the meaning of the answer. Now the schema here tells me in this one, this was a 6th grade problem, that I'm trying to do division. And so I'm trying to see how many 3/4 pieces of cloth I can get from 5 meters. So if you think you can, from your drawing, you can get that answer, why did you type your answer into the chat? Interesting. Very, very good answer. You're going to be able, you've all got that one. We're going to be able to make 6 craft items. But when we write our answer, how we write the answer is deceptive. So now I'm going to go to my document camera and I'm going to discuss the meaning of the remainder. All right, because this is really critical at this level. So here's my drawing, and I could do the same on the number line. And I see that, yes, I can get 1, 2, 3, 4, 5, 6 of my craft items. But how I name the remainder is the critical piece. And I'm going to go back to my, let me see if it's still out here from yesterday. I think I put it away. I want to go back to my strings with wings. And see if I can make this language clear, because it is a very, very important piece of language for division. I'm working in a very small space. Oh, and I didn't think, oh, yes, I did. I didn't think I was going to have that in this presentation, but I'll do it anyway. In division, the meaning of the remainder is always written in terms of its relationship to the divisor. In multiplication of fractions, the reasoning is that the answer is named in terms of the whole. But in this case, in division, I want you to think about, let me give another example here. So I have 7 dots there. And if I say that I want to know how many groups of 2 can I make, the measurement model is that I can make 2 groups of 3, and then I have a remainder of 1. But by 6th grades, students need to name that remainder as a fraction of the divisor. So it's 2 1/3. Now in fraction division, this is 2 of the 3 I'm trying to make. So the answer, even though it looks like it's 1/2, the answer is 2 of the 3/4 I'm trying to make. So the answer to this problem, when you do the algorithm for division of fractions, you're going to get 6 2/3, and that's why. Because the remainder is what part of 3/4, and it's 2/3 of 3/4. So we're not going to name the remainder as 2/4 or 1/2. It's 2/3 of the 3/4 I'm trying to make. And that language starts with division of whole numbers. And then we take that to the fraction level. I can demonstrate that in a different session on division of fractions. But the critical piece is knowing that the remainder is always named in terms of the divisor, not the whole. Okay, so drawing boxes, a number line, it works well for that problem. This is as my student did it. So he did it with the squares, and then he did it with the number line as repeated subtraction. So just as linking multiplication to repeated addition, 5 groups of the quantity 3/4, but I'm making 6 2/3 groups of the quantity 3/4. So doing it in the number line for some students will be a little problematic. Okay, great. So strong evidence is that we want to assist students in monitoring and reflecting, and that's what I'm hoping I'm teaching you to do. If we deal with word problems in small pieces, we are better able to do those small pieces. Now, Dr. Eileen Marzola, who's a specialist in reading comprehension, says for stories and fictional text and everything, you think before, you think along, you think after. Now, we've all heard activate prior knowledge. In word problems, I like to say that first sentence sets the context for the problem. Do I understand what brownies are? Do I understand what boxes of cookies are? Do I understand cutting pieces off of a length of cloth? That's your think before. And for math word problems, I say do along so that you do not have to keep all that information in long-term, short-term memory. So you're going to calculate, you're going to draw, you're going to calculate as you go along, and you'll see that it's going to help you to better monitor what you do and reflect on it as you go through. So the student with language-based problems or second language learners will be easily overwhelmed. So the problem with word problems can be attributed to that lack of awareness and instruction in grammar and syntax as well, the punctuation marks, and that we need to work on efficient comprehension, which depends on 96% accurate reading of the words, but with appropriate prosody. The phrasing of the language will determine whether the students understand the meaning of the problem. That's where, if we just say read and understand the problem, lots of our kids don't know how to read the problem. And so add working memory to that mix, and you've got the perfect storm when reading and math meet. I want to skip over a couple of these problems because I want to get to the big one. In fact, I think this is it. So this is where organizing your thoughts incrementally can be very helpful. A grocery store had cans of soup on 7 different shelves. Draw something, people. I hope you drew 7 shelves. The bottom 4 shelves each had 29 cans. Are we going to draw the cans? No, we're not Michelangelo. And if we're going to think and calculate along, what operation do I think I might need to figure out? Do you think reasoning that I might have to know how many cans are on all the shelves? Would that help me? Quite possibly. Could I do that a number of ways? Could I do a traditional multiplication algorithm? I could. Could I do repeated subtraction? I could. Could I use the area model of multiplication, the box model, and do that with place value based? I'm going to model that with 4 times the quantity, 20 plus 9, using an area model multiplication model. I know that 4 times 20 is 80. I know that 4 times 9 is 36. I put those two together. I flexibly break 36 into 20 plus 16, and I get 116. Simple, stupid, fast. Next component. I've got that locked. I'm going to put it down here. Next sentence. The top 3 shelves had 42 cans. Might I have to know the total number of cans, do you think? Quite probably. Let's figure out what that is, however you want to calculate it. Now, reasoning. Do you think I'm going to have to know the total number of cans on both those shelves? I'm thinking here that could be the question that's going to be asked. I'm going to go ahead and calculate 126 plus 118. Is that correct? Tell me if I'm going too fast and messing up. Got that one? 80. Okay. I'm rushing here, so tell me if I'm right. What's our total? Type it in the chat. Let me see. What's the total number? $244. 242. Let's check that out. 242. We got a consensus 242. I'm going too fast. Yes. Okay. Yeah, that's where I blew it up. It's not 36, it's 32. 240, 242. I knew I did something wrong because I'm going too fast. Okay. So now, yes, because now that could be the first question, the total number of cans on the shelves. But this is math, people. This is 6th grade. Nobody's that nice. After 56 cans of soup were sold. What does that mean? What's happening to those cans? Are they being added to something? Now's where the schema comes in. What do you think you're going to have to do? Type it in the chat. What might we have to do now if 56 cans of soup were sold? Subtract. So 242 minus 56. Notice this is math torture because now I have to regroup in subtraction. I got 5th graders at this point. They see that whole thing as a paragraph, mark C and move on. So I'm going to have to regroup twice. And for the first time, I may have friendly numbers. The display case had shelves that could each hold 9 cans. Each. Each shelf holds 9 cans. What schema, what operation might I have to do there? Yes. So I do my division. Now I've had all 4 operations with subtraction, with regrouping. Is this going to be a friendly number division or not? How many shelves will I need to fit all the cans? Type your answer into the chat. How many? I've got divided by 9. $186 divided by 9. I'm going really fast here, folks. How are we getting 21? We have not 56 divided by 9. A clerk moved the remaining cans to the display shelf. So no, we're not doing 56 divided by 9. What remaining cans were moved to the shelf? We moved 180 some cans to the shelf divided by 9. Yeah. Now, Janet, you're really on the target here. Can you express that remainder as a fraction of the divisor? So you see, well, no, you don't have a remainder. Janet, you need to have, we have remainder 6. Amy, you got it. Janet, you got it. But we need all the cans to go on shelves. Yes, exactly. I have to have 21 shelves because I need a shelf for that remaining cans of 6. So do you see how if we do this incrementally, our students really can see how to catch up and organize their thinking. Now, the way I've set this out, I usually do this even a little more cautiously here. But what I do is the student would then be able to show me their thinking, and the student would be able to tell me what they did from the shelves to each calculation as they go toward the answer. We need 21 shelves. And this is where we want the student to answer the question in a complete sentence and be able to describe their answer and reason. Okay, wait a minute. I got to stop sharing here. I'm about to hit the wrong button. Where's my stop share? Nope. Oh, that's what it's happened. Okay, it's up here. I'm hitting the wrong place. Thank you. Okay, stop share. So if the student organizes their thinking as they do the calculations, they will be able to talk you through how they reasoned the answer. And they can check their calculations at every step. So even in these multi-step problems that occur in 5th grade, all right, and that Mandy's got the great question. How do we get those students to not just select C and break it down like this? You don't show them the whole word problem. The answer is practice doing word problems incrementally using PowerPoint and only show them part of the problem and make them reason and draw and calculate as they go along. And the student will only buy into it. This is from the great essay about how does change happen. If it is beneficial to the individual, they will adapt and change. If it's not beneficial to them, they just go on doing the same old, same old. So the structured procedure is to stop at the punctuation marks, okay? Stop at the punctuation marks and think, calculate, and draw. So that's think before, think along, or do along, and think after. So as I do this with each unit I do with my students, I make them do this incremental practice. And some students who don't need to do it can read the whole problem and calculate as they go along, and they're fine. But for the student who needs those structured procedures, that's where you get them in a habit of highlighting or marking the punctuation, pausing and thinking, and going on. And what sells them on this, and Mandy, I love your question, what sells them on it is that they've become successful. And yes, Cassie, it's a big problem. And I use this, I do have algebraic models in this. I think I have about 8 minutes more. Is that correct, Lauren? Got about 8 minutes more.
That is right.
I'm
Actually, six
rushing through.
minutes.
So I'm going to show
Yes,
you
6
just a
minutes.
couple more. I do want to show you a couple more of these. Stopping to do this with you is really important because I want you to see the methodology. So did we practice our incremental, sequential, cumulative, and thorough reflection? And those, by the way, those words come from Orton Gillingham in literacy. Incremental, sequential, cumulative, and thorough. Did we create efficient representations? Did we utilize several problem-solving strategies for our calculations? Whatever the student is efficiently able to use, box model, standard algorithm, number lines. Did we adapt and modify as we work? Did we use a metacognitive strategy? One student likes that area model for multiplication, and at the algebraic level, the box model is used all the way up to polynomials. Did we use our 4 superpowers? Did we think flexibly? Did we use our idea of numeracy and decomposition of numbers? We did. So faced with that paragraph problem, we don't want them. This is the same problem you just did. That's mark C and move on. We don't want them marking C and moving on, because if we've taught those 4 basic operations and they can generate the problems, I mean, the fluency, their students should be able to solve this problem. But they need to understand that that final shelf needs, that final set of cans, that remainder needs a shelf. And on the fraction one, they need to know how to respond to the remainder being a fraction of the divisor. So moderate evidence has helped them to recognize and articulate mathematical concepts. I do constant rate of change and starting value. We label it. We write our word sentence of slope-intercept form. That's one representation, and it's student-friendly language. what happens over and over and over again. And what do we start with that doesn't change? Given that they can solve word problems. So Jamie was given $100 for his birthday. You write $100. He decided to save money, money for a snowboard he wanted. He planned to put $100 in his piggy bank. He did that. So $100, I draw the piggy bank, and he adds $20 from his allowance each month. Now that one in algebraic thinking can actually be represented in something that's kind of like a bucket model. And it just cues them into the leading coefficient. So I might have them draw these little buckets as a representation early on. This is not your final representation for linear functions, but it's a possibility to get them into that thinking. So we might have them doing $100 and then 20, 20, 20 to get them to that constant rate of change. Then we want them to drop that into slope-intercept form for our word problem. So there are a lot of ways to use these visuals to help them understand the context of the problem. So the slope-intercept form is widely used on those algebra and pre-algebra exams in middle school. Renting a car, down payment and payment plan, your cell phone plan, you're joining a gym, Pop's Gym, memberships, depleting your savings. So you get a lot of these different things that are going to help you to fill out our table of values. Make sure your middle school students always use both horizontal and vertical and can use either one fluently. And so the strategies for that algebraic notation, again, we're looking at the words. Carly has $12 to spend. Write $12 down. She must buy 1 gallon of milk, right? You write a number sentence, you write your inequality, and then you can take it down incrementally to solving it. All right? And I think, Lauren, I'm right at the end, right? Minimal evidence is what we all do. When you show them how to do one problem, you've shown them how to do one problem. So in the handout, I haven't given you my slides. I don't do that on this one, but I have given you these for the presentation. Our last one was an elementary one, and I'm going to stop there because we're at the end of our time. But I hope this has been helpful for you to get that idea that you need to be able to give your students alternative problem solving strategies when too much language is too much for those children with working memory issues. The hand gestures, I have to tell you, I just do them. You have to think, that what are you illustrating conceptually? But I will tell you, the research tells us that the gestures you use or have them use must be embedded in the instruction and explicate some aspect of the concept. So it's not just a gesture for some sort of letters or what you do in order. It has to show you some concept. And so leading you to your procedure, those are things that I just do incrementally.